Is that percentage a p or a p hat? P hat. And so this one is like roughly here. And then this one is like roughly here. And then here. And I keep going, and I keep going. And at this point, you guys, I've done a bunch of these, okay? Between all the 4 different class periods. If I gave you this picture of my p hats, and I said, all right, guys, what percent of this bin is red based on this graph? What would you say? Roughly, you might say, hey, the actual value for P is right here in the middle. Is everybody good? And you would be close. I think it's supposed to be roughly 71%, though I've certainly lost some over time, and I don't know if I've lost them proportionally. So potentially it's not 71% anymore, but it should have been pretty darn close to 71%. Okay? Now, this is an example of what's called an unbiased estimator. And what makes this statistic an unbiased estimator is essentially that of the mean of all the statistics, the mean of the p hats or the mean of the x bars is equal to the parameter you're trying to estimate. Okay? And what usually happens in order for that to happen is, yeah, sometimes my sample is going to be bigger than P. Sometimes my sample is going to be smaller than P. But they're going to average out if I did it over and over and over again. It would equal P. All right, so I want you to think through. We're going to kind of talk about what is a biased estimator as well. Okay. Now, when we talk about biased estimator, we're talking about whatever we're choosing to use to make the estimate. And where this gets kind of weird, okay, is just because we can doesn't mean we should. So, who's the tallest person in the room, you think? It's probably Ryan, yeah? Ryan, how tall are you? 6'2". 6'2"? Who's the shortest in the room? How tall are you? 5'2". 5'2"? Yeah, like 5'2". 5'2", yeah. So we got lots of 5'2s, yeah? Okay, so you guys, if I asked you what is if we were to think of ourselves as a population, what is the range of our population in height? 5'2" and 6'2". Remember, the range, what we do is we subtract, right? So if I say that the range of our population is 12 inches, are we comfortable with that idea? All right, now, let's pretend that do you think I could take a random sample? Like, we could throw everybody's name, throw it in a hat, mix it up really, really well. I'm going to pick out 2 people. Is my sampling method good, by the way, if I do it that way? As long as it's really mixed up and everything? Drawing names out of a hat? Yeah. Yeah. Will it be a good estimator of the range of my population? No. Why? That the only way and if I were to make a graph, and I'm going to use a little r to represent the sample range. It's not really like a thing that we have a sample range and a population range that we actually do anything with because it would be an unbiased estimator. But let's go ahead and say, what are the possible sample ranges we could get? Well, our sample of 2 people, let's go say we're just sample 2 people, could be Ellie and Chloe. And if that is the case, what is the range going to be? They're the same height, yeah? So the range would be 0. And then I take another sample, and this time it's going to be Nate and Daria. How far apart are your guys' heights, do you think, give or take? Inch or 2? 5'6". 5'6". Oh, another 0. Right on. Okay, then it's going to be Math and Meister. We'd probably see at least a little bit of a difference in height there, right? Do you guys catch what's going on here now? Okay, and so maybe that one is here, And Math, how tall are you?
6 foot.
6 foot. So I was going for about, thinking it was about 10-inch height difference. Okay. All right. And now every once in a while, we might get that 12, right? Because we could get the random sample that is Ryan and Meister, right? That could happen. Okay. But overall, my sample ranges are going to be all over the place, lower than 12. And on average, the sample range underestimates the population range. So is the sample range a good estimator of the population range? No. It is a biased estimator. How is it biased? It underestimates. Do you guys kind of see what's going on there? Okay? That in order for an estimator to be unbiased, you should have as many above it as you have below it. Like the sample values, those statistics. Okay, now I want to talk about bias a little bit more because there's a misconception that happens every single year where kids say, oh, my sample size is too small, it's biased. You guys, the size of a sample has nothing to do with bias. If I would have taken a sample of 4 of us instead of 2 of us, would the range still be biased? Do you guys see what I'm saying? That estimator is biased no matter how big the sample is. Okay? So, sample size has nothing to do with bias. Nothing. The sample size has nothing to do with bias. Now, what does sample size have everything to do with? Well, larger samples have smaller standard deviations. I don't like the way I worded that at all. Hold on. Larger samples, sorry y'all, have less variability in the statistic itself. And I really don't like the way that plays. And here's why I want to be very, very careful. If I take a larger sample, I'm not saying that the standard deviation of that sample will get smaller. I'm saying that whatever I'm measuring from that sample, so if it's X bars, I'm not saying any one of these, like, for every one of these samples, there's a mean and a standard deviation. The standard deviation of a singular sample doesn't have anything to do with the size of the sample, okay? The standard deviation of all the possible sample means is what has less variability. It's the statistic that has less variability. Now, yesterday we were kind of looked at a distribution of X bar, and today we're looking at X bars and P hats. And the mean of the X bars is mu, and the mean of the P hats is P. And the reason that in a standard statistics course we deal with X bar and P hat is because they are unbiased estimators. That's why we choose them to begin with. Okay? So why would we want our sampling distribution to have less variability? Are you guys with me that less variability just really means smaller standard deviation? That's the same thing, yeah? But can somebody remind me, what does standard deviation actually mean? Average distance from the mean. Now, are you guys with me? If I look at this graph, isn't the average distance from the mean going to be the average distance between X bar and mu? Do you guys get what I'm saying here? So we would have that smaller standard deviation would equal smaller distance between x bar and mu. And since my job in doing all of this is I'm trying to use x bar to estimate mu, wouldn't we want that distance to be smaller? I could have said smaller distance between p hat and p. Same idea. Did you guys catch my drift? All right, so for the rest of the class, we're going to focus on specifically when my statistic is a p hat to estimate p. Now, it's a little bit early, but are you guys with me that the greatest kind of day without school is a snow day? Mm-hmm. It's a little too early to hope for it, but because if we have a Monday off, I usually I should do this on that day and this on that day, but when it's a snow day, I get just to do nothing because I have nothing planned for that time. It's way better than a planned day off. You guys get what I'm saying? So it turns out that anytime there's a storm coming through, I flush ice cubes down my toilet. I sleep with a spoon underneath my pillow. I put my PJs on inside out. Because snow day superstitions, I don't really believe in them. But why take the chance? You know what I'm saying? Why take the chance? So, have you guys heard of this, flush ice cubes down the toilet?
No. I've heard of none of those things. I've heard of all of those. Well, my parents.
Your parents are teachers. That might make a difference. I had never heard of the spoon under the pillow until I started teaching in Grandview. That was new to me.
I don't know. You just pick them up.
Does anybody have a different snow day superstition?
Religiously check in.
Yeah, religiously checking's bad.
Yeah, that's the worst way to do it, right? That's I always, when I was a student, I always did all my homework because I was if I know it's my luck that if I was oh, we're not going to have school tomorrow, I don't need to do this until tomorrow, that they wouldn't call school. You know what I'm saying? Yeah, man. I don't think, it's pretty rare to get one in December, but I don't think we're past the point of hoping, right? I think we've gotten to the point where we can start checking the forecast in advance and be oh, maybe in a week, but we'll see. You guys. So let's go ahead and say that for all of the students in Grandview Heights High School, 65% agree with the statement, if you flush ice cubes down the toilet during a snowstorm, school will be canceled the next day. So, you guys, that 65%, is it a P or a P hat? P. Because?
All the students.
It's all students. Cool. All right, so we're going to operate under this assumption that our P is 0.65. All right, so now, I'm sampling from a population where P equals 0.65, and I'm going to take a random sample of 5 students. So are you guys cool if I call that N equals 5? And let's go ahead and just let X equal the number of students who in my sample who agree. Is everybody with me? If that's my variable, how is it distributed? We have an N. We have a P. Binomially. Is everybody with me? All right. So could we come up with this probability distribution for this binomial random variable? Okay. So can everybody just pick one and somebody figure out what's the probability X equals 0. Somebody figure out the probability X equals 2. I don't remember them. Do you guys see what I'm saying there? As soon as you have one, just say, oh, 2 is this probability. I'm sorry?
3 is
0.33, cool.
4 is 0.31.
.04. Cool.
0.05.
Cool.
It was 0.18.
5 is what?
I was one.
No.
Feel that
You should be doing PDF, not CDF.
Yeah.
I got 5 is 0.11.
0.11.
1, 2.
1, 2. Okay. And then
0.05. 0.05.
cool. Now, y'all, if it's binomial, does it have a pretty easy mean and standard deviation? Because don't we even have formulas for the mean and the standard deviation of a binomial? The mean of a binomial is n times p. The standard deviation of a binomial is the square root of n p 1 minus p. Is that pretty good? So the mean of my binomial would be 5 times 0.65, which is something. And the mean and the standard deviation of my binomial would be the square root of 5.65, 0.35. And I know this one's 3.25. I don't remember the standard deviation. You're making me yawn. Are you sure? Yeah. Did you do 0.25 instead of... Everybody good? Now, you guys. Don't we kind of end up with this, like... Couldn't we turn those into percents? Like, I have the sample of 5 people. If one person agrees with the statement, could I turn that one person into a percent of the sample? And if so, how would I do that? If one person agrees with the statement, what percent of the sample agrees with the statement? 20. How'd you get that? 1/5. Oh, so you divided by 5? And if 2 people agree with the statement, that would be 2/5. So to turn any one of these values into a p hat, wouldn't that p hat just become the number of successes divided by my sample size at any given time? That's what p hat is. The percent of my sample divided by the size of my sample. Or the number of successes in my sample divided by the size of my sample. And if I divide an entire distribution by 5, what's going to happen to the mean? It's going to get divided by 5. What about the standard deviation? Divided by 5. Because when I multiply or divide, both the mean and the standard deviation change, yeah? So, my mean of the p hats, notice I'm using a different symbol now because it's a different statistic. It's not my number of successes, it's my percent of success in my sample. That would be 0.65. And my standard deviation would be whatever 1.07 divided by 5 is, which is going to be like, I think it's like 0.21-ish. Ish.
Is it just a coincidence that the mean is the same as the probability of like success?
So, the mean of the binomial was NP, yes? Is everybody with me? And then to turn that p, or that mean, or like to turn that binomial into a p hat, I would divide by n, yes? So is it just a coincidence? No. The mean of all p hats is always p. Likewise, the standard deviation of the binomial is the square root of n p 1 minus p. And if I divide that whole thing by n, because that's what you do, we get a new formula that's very much related to it. I'm going to write it a little bit different than the way that looks, though. It would become p 1 minus p all divided by n, and that n is part of what's underneath that square root. I don't have you convinced that that's what it is, do I?
Well, I'm just confused how that's the same as.
Okay, you're right. What if I took that n out and wrote it as the square root of n squared? So that I have a square root and a square root.
Sure.
And if that's the case, what do I do with my exponents? Subtract. So the reason I might do that is it becomes now the square root of n p 1 minus p. Like I can write it as one square root sign. But then n over n squared would just become n to the 1 on the bottom. That's an approach to look at it. And y'all, these two formulas are in fact on your formula sheet. So you will never have to memorize them. Okay? Now, there's one other thing that happens. Remember yesterday as we took the larger sample, like when n was equal to 50, my sampling distribution became normal? Okay? So under certain circumstances, the sampling distribution of p hats will be normal. Those circumstances look like this. You're going to do np and see if it's that greater than or equal to 10. And if it is, then my sample size is large enough that the sampling distribution will be approximately normal. Except for it's not just NP. Two things have to happen. NP and N1 minus P has to be greater than or equal to 10. And if that's the case, we can say that those P hats will be approximately normal. Okay. This, not on your formula sheet. That's something you need to memorize. Now, I'm hopeful that we will have plenty of practice with that and it won't be a big deal. .02. All right. Okay, so again, this is just me formally typing the formulas. You don't need to pay attention to that. And the p hats will be normal when np and n1 minus p greater than or equal to 10, and it's both. It's not one or the other. It has to be both of those things have to be true. Okay. So we're going to do 2 example problems, and then you should have some time to work on test corrections if you still need to be working on those, okay? All right, so let's go ahead and say 75% of young adult internet users are watching online video, and suppose that we take a sample survey and contact a simple random sample of 1,000 young adult internet users and find the p hat of that sample. Y'all, tell me something I know here. What are some of the key characteristics that we should be writing down from this? N equals 1,000. I have a sample size of 1,000 and P equals 0.75. So I'm going to take a sample of 1,000 people Now, of that sample, is it going to be exactly 75%? Nah. So I could have a sample where it's only 700. So 70%. I could have a sample where it's 80%. But overall, what is the mean of all those p hats going to be? 0.75. All right. And what's the standard deviation of those p hats going to be? Well, if it's a standard deviation, are we all cool it's going to have a square root in it? And what should I put underneath that square root? .75, 0.25, and 1,000. And I don't remember what the answer is. If I were to guess, 1.5%, 0.015. 0.014. What about the shape? Do you think it'll be normal? Let's check. How do we check it? We do NP N1 minus P, 750 and 250. Are those greater than or equal to 10? Do you guys recognize that this is essentially shape, center, and spread? All right, I'm going to change the rules on you. What if instead I said n equaled 9,000? So I multiplied my sample size by 9. What will change? What will stay the same? Will the mean change if I multiply my sample size by 9?
Yes. No.
The mean is the percent of my population. Does the population change depending on how big my sample is? Nah. Nah. So the mean would stay the same. It would still be 0.75. What about the standard deviation? Would the standard deviation change if my sample size was 9,000? Yeah. So my question to you guys is, if it's 9,000, how will my standard deviation change? It will get smaller. How much smaller? A lot smaller?
1/9 of what it was before.
Let's see. 1/9 of 0.014 is
The root of 1/9 is
0.0016. But that's not what we'd get. We'd end up getting 0.005. And here's what happens. You see that 9 that I multiplied by? It's underneath the square root sign. So not only is my standard deviation getting smaller, but it's getting smaller by the standard deviation of 9. Or by the square root of 9, not the 9 itself. Because the sample size is underneath the square root sign. Okay? All right. One more example. Guys, you can see I maybe had an issue where I I hit return 1 too many times, so that 9,000 question that we just did was written at the top of the next page, but it's not supposed to. All right. Polling organization would asks a simple random sample of 1,500 kids. Sorry. First-year college students, how far away their home is. Suppose that 35% of all first-year students actually attended college within 50 miles of home. what is the probability that a random sample of 1,500 students will give a result within 2% of this true value? So the idea is, how reliable is my sample? Okay, what's the probability my sample will be close enough, and we're defining close enough as 2% to that 35%. Okay, everybody with me? All right, now, normal condition first, we'll do 15,000 times 0.35. I said 15,000, I meant 1,500. 1,500 times 0.65. If you need to go out in the hallway for a second, it's all good. No worries. Guys, I think these are 525 and 975. So, is the sampling? Are those p-hats going to be close to normal? They sure are. All right, now, what is the mean of my p-hats? You know what? I'll calculate the mean. You guys find the standard deviation. That was funny.
Yeah.
You guys, I got it. I got it. I hate it when that happens. If I eat spicy foods in particular and I get all sniffly, and then I cough, and then my coughing makes me cough more. Hate it. Hey guys, what's the answer to the standard deviation here? 0.012. That's what I got.
Same thing. Wow. Okay, I actually seriously.
All right. So, jeez. We said that the mean is 0.35. We said it's approximately normal. Whoa, that was going to bother me. Oh my gosh.
Any of you guys have this new sickness thing? I caught it last week. It was not yet.
Yeah, whatever it is,
We're gonna have to go back to virtual school.
God, I hope not. Yeah.
I'm not leaving. It's okay.
All right, y'all. So these are all my possible samples. If I want to know what is the probability I am within 2%. Which of my samples would be, what could we say about the value of my sample p-hat if it is within 2% of 35?
It's good.
Yeah, but what possible values are within 2% of the 35%?
33%.
Yes, it could be as low as 0.33 and as high as 0.37. So if I want to know, as Daria said, if it's within 2%, it's a good sample. Yeah? So what's the probability? If that's how I define good, right? So in the real world, what we do is we say, how close do we want to be, right? What wiggle room are we willing to accept? Okay? And after that, if my sampling distribution is normal, with a mean and a standard deviation, right? If that's the case, can't I just use normal CDF to get there? This is why we like normality. It's why we like having the patterns that these p-hats follow. I'm pretty sure the answer is 90%. So if I wanted my sample to be within 2% of the actual value, I'm in a pretty good shape because it's going to happen 90% of the time. Now, Something that's worth noting, in the real world, we don't know the 35%. You wouldn't take a sample if you knew the answer to what the true percentage was, okay? But the goal of Unit 5 is saying, like, hey, we can see these patterns, and then starting in Unit 6, we're going to be like, okay, when all I have is a p-hat, what can we conclude?
I was wondering